Hi, everyone. First, thanks for thanks for your work on the test yesterday. I got emails from many of you uh, citing issues with file uploads, that there was a limit, and then that it would only allow you to upload one file, and then once you had uploaded one, then it sort of didn't want to accept anymore, and um, I I got all your emails, so no worries there. In the future, I'll ask you to please do plan to upload one document, one file with all of your images or whatever it is. If that's a Word document into which you have put all of your images, or if it's like a zip file or some kind of compressed single file that contains a whole bunch of image files within it, that's okay too. Um, if if you need help figuring out how to do that, how to make one file that you can upload to a submission like that, let me know in advance of the next test so that we can kind of walk through that together and make sure that the process makes sense. Um, Other nuts and bolts type stuff. Um, I will try to grade and post this midterm as quickly as I can, um, along with some other things that I still have to post as well. And remember that we still have mastering physics due on Sunday, and I'll be posting this week's assignments soon. Should go up right after this video goes up, in fact. So the first thing we have to do for content this week is to sort of finish our discussion of oscillation. And the next thing we want to talk about is a particular application of simple harmonic motion, the oscillation that we developed in the last lecture. So I'll refresh our memory a little bit and then look at another example and apply what we had from last week to this new example, and we'll go from there. Remember that we had, we had said at one point that we have a differential equation to solve, and we ended up saying that the acceleration was negative proportional to the displacement, that as long as the acceleration and the displacement are negative proportional, that the constant of proportionality is related to the angular frequency of the thing, equals, in the case of a spring, it was root k over m. And we use that in F and 1 over the period to figure out relationships for the period. Just refreshing our memory that that's an equation we had for the Hooke's Law lab, relating the period of the oscillation of a mass at the end of a spring to the mass in the spring constant. And last week we said that anytime we can show this, anytime that the acceleration is equal to negative smiley face x, anytime we can say that, that must mean that this is an equation that describes oscillation, some kind of simple harmonic motion. And since smiley face lives where omega squared usually lives, then we're forced to conclude that smiley face is omega squared, or that there is some angular frequency omega associated with, remember this, like Platonic imaginary rotation, some actual angular frequency in terms of smiley face, in terms of whatever expression lives here. Anytime we can cast the acceleration as negative proportional to the displacement, what we've got is simple harmonic motion. And the one of the applications that we want to talk about for that is a simple pendulum. In a simple pendulum, we're going to assume that there's a mass m at the end of a string that has a length L, and that the string's mass is negligible. Compared to the mass at the end, it's irrelevant. What we've got is a mass L away from a point at which the whole thing rotates around. So we'll have some sort of circular arc if we drag the mass up to some angle here, angle from vertical theta. And we let go, we know from experience that it'll swing down through equilibrium, whatever, we could talk about the energetics actually. We know that there's some delta H here. So whatever potential energy we have at the start of the swing, we'll have that much kinetic energy once it reaches the bottom. And then we'll have kinetic energy that'll carry us up through the same height on the other side and back. And we'll get this motion back and forth, this periodic motion. And we can call that periodic, we can call it oscillation, but the question is it simple harmonic motion? Is it motion such that we can just use all of the conclusions that we developed last week to describe it? Well, in order to figure that out, we have to figure out what Newton's second law looks like. The sum of the forces should be the mass times the acceleration. In this configuration, let's draw a free body diagram. We know that there is gravity, and we know that there is a force along the string, tension. Let's assume that we're doing this in a vacuum, so we don't have to worry about the air resistance, and that's the whole story. Okay, well, what is the tension equal to? And the trick is, I think it depends. If we choose that coordinate system, so we've got the x-axis this way and the y-axis this way, then we know that the y component of gravity, Fgy, has to be equal to tension because it isn't accelerating along that axis. If it's accelerating at all, it's doing so along a circular path, always tangent to the circle. In other words, always perpendicular to the radial direction. So we know that the sum of the forces in the y direction, this y direction, needs to be 0, which means the tension needs to be equal to Fgy. Now, this angle is theta, so is this angle. And then the y component here is the adjacent side. So this is hypotenuse cosine of the angle. Okay, so the tension Yeah, there it is. mg cosine. Oh, well, okay. So now we know what the tension is, but what about the missing piece of gravity? What about the other component of gravity? Because there's no way for that component to be canceled by the tension. If we're going to have net force, I think that's where it comes from. That the only component that is net isn't canceled by anything else is the x component of gravity. In other words, mg, not cosine, but sine. And that's the net force here. So this is, okay, mg sine theta equals ma. I've got a mass on both sides. So this equation looks like A equals G sine theta. So this doesn't look to me like simple harmonic motion because we haven't said that the acceleration is negative proportional somehow. Smiley face squared, I guess, omega squared, whatever it turns out to be. I'll just leave it smiley face. Negative somehow proportional to some kind of displacement. Now, well, the positive x direction points this way. That's how I drew it. So this, that goes the other way, that should have been negative all along. That's my bad. So at least we've got the minus sign that we want. But it's not proportional to position. It's proportional to, and it's not even proportional to angle either. It's proportional to the sine of the angle. And we know that sine is a nonlinear thing. So this is not quite, not quite simple harmonic motion. Unless we're able to show somehow that sine theta is basically theta. Now, well, let's look at theta and sine theta. Let's do that in radians because that's the unit of angle that actually makes sense. So here's a graph of sine of x and x. X is in blue and sine of x is in red. And these don't look particularly equal. We've got this one is 1.5 and this one is 1. So we're talking about 50% difference. So yeah, but I'm looking at the middle of the graph here, and in the middle of the graph, they do actually look really similar. So what if I restrict the size of the x-axis? And again, let's do this in radians. So what if we go halfway, pi over 2? Is it okay? So if this is the only window we allow for ourselves, then these two graphs look much more equal. much more the same, at least, than they did a minute ago. And if we restrict ourselves even farther, let's say, so instead of pi over 2, that's 90 degrees. So we're talking about the entire, negative 90 to 90 degrees. What if we talk about, because remember, negative 90 to 90, that's the entire bottom hemisphere here. If we let theta go from positive pi over 2 all the way through to negative pi over 2, that's the entire possible swing. What if we go a little bit narrower? What if we only talk about kind of small oscillations one side or the other, maybe 30 degrees, pi over 6? Wow. So on the red curve at negative 0.5, we're talking about negative 0.479. And on the blue curve, well, the blue curve is y equals x. So at negative 0.5, y is negative 0.5. So we're comparing negative 0.5 to negative 0.479. Those are really close. Like, I mean, a percent or 3, maybe. So just to be safe, what if we got half of that again? What if we went from, instead of 30 degrees, what if we talked about 15 degrees? So pi over 12. See, we can't even see the difference anymore. Those are essentially the same graph. I mean, I can't tell the difference. Maybe if we zoom in a little bit and like only go to point 0.4. Maybe if we zoom in a little bit, negative 0.4 to positive 0.4. Okay. So maybe down here at the very, very edge, we can see a little bit of difference between red and blue. So maybe not. No, so 15 degrees is okay. This is 15 to 15. Maybe what if we go to negative 10? Just 10 degrees one side or the other. So that's pi over 18. Pi over 18. And let's look at this from negative 0.2 to 2. These are so similar. I think as long as we're talking about radians and as long as theta stays smaller than pi over 18, then sine theta is about equal to theta. And this is my graph that proves that. What do you all think about that? We'll call this the small angle approximation. Okay. So we'll keep this in our pocket here, and let me make a couple edits to my drawing here so that we can actually, maybe we can still get it to look like that. I'm going to change the axes to be a little bit more normal, just up, down, left, right. We've got our vertical axis this way and our horizontal axis this way. So this distance is our x-coordinate in this system. But that distance, it's part of a right triangle made with angle theta and the length of the string L. So I think this distance, the x-coordinate in this coordinate system, is L sine theta. Okay. But as long as we're talking about a small angle, sine theta is about equal to theta, I guess. About equal to. Sine theta is about equal to theta. And theta, if we divide both sides by L, negative g x over L. Which looks a lot like negative stuff times x, where this stuff should be a equals negative omega squared x. So this thing in a box, it lives in the same spot where omega squared lives, and we've got something that is, because gravity isn't changing, L isn't changing, this is a constant thing, just like omega was in terms of K and M, negative proportional to the displacement. As long as we're talking about small amplitude swings. As long as we stay within about 10 degrees, one side or the other, then we can show, or at least we can argue, that pendulum motion is, for small angles, just simple harmonic motion. As soon as we can say this, we can immediately rely on everything we said last week. As soon as we say this, A equals negative G over L x, well, that means omega is square root G over L, which means our, let's see, so we could use the same, omega is 2 pi f, or capital T is 2 pi over omega, so this is 2 pi root L over G, so we've got that formula there. We know now our formulas for position, velocity, and acceleration, they all depend on omega. So our position now depends on, so it's some amplitude, x max, I guess, cosine omega t, where omega is square root G over L. And we know that. We know the velocity. We know the acceleration. This is great. You're able to do this because we can show that if this is the template for simple harmonic motion, as long as we're going to talk about small angles, we can match pendulum motion to that template, and everything we said last week still applies. This week's lab is about pendulums. So we'll, sort of like Hooke's law, we've got two parts. The first part is to assess this dependence. How does the period of a pendulum swing depend on length for small amplitudes? The other part, it gets at assessing the small amplitude part of that. What if we use an amplitude that's too big? What happens to the period? How different does it get from the small angle approximation sort of theoretical value? Okay, that's it for this application. Um, let's see what's next.